Part 2 of Section 3.2, Power Series and the Ratio Test. The monomial basis for analytic functions is given by the collection of monomial terms, 1, x squared, and so on. An analytic function is a function which can be differentiated infinitely many times. So analytic functions are smooth functions. Okay, here we define power series. A power series about x equals 0 is a series of form given in this equation. Constant c1x plus c2x squared plus and so on. That is nth order term and go on infinitely many terms. And a power series about x equals a is a series of the form here. Rather than x, we are using x minus a. So c0 plus c1 x minus a, c2 times x minus a squared, and nth order term is cn times x minus a to the n. Now continue here. Such function and such a collection of terms is called a power series. Once it is about 0, so using x only, then it's about x equals 0. Once terms are combined along with x minus a, then we say a power series about x is a. In this case, a is the center of the series, and now c1 to cn, and these are the coefficients. Okay, that is definition. Now we'll see here, taking all the coefficients to be 1 in this series, and we can get the following geometric series. xn, n is from 0 to infinity. That is given in this way. Now this summation series converges to 1 over 1 minus x only if the absolute value of x is less than 1. That means that here this series is the same as 1 over 1 minus x when absolute value of x is less than 1. You can check it quite easily, and if you try to multiply this term and that one, then you can check it. Okay, for example, we try to multiply two of them, then there is now 1 minus x, and here 1 plus x squared plus and so on, like that. Okay, then here this is the same as along with 1, the same as 1 plus x squared plus now, and along with this one, second one, there's minus x and plus here now and minus x squared. Okay, rather than plus, we put here minus now x squared and minus x cubed and so on, so that we can cancel out. In fact, we have to do this one in this way. Now the last term is xn, then there will be here the xn, and this one will be minus xn plus 1 power. And now if we simplify this one, there will be 1 minus x to the n minus 1. Now we take the limit and n approaches infinity. Now once we take a limit, then once x is larger than 1 or the length is 1, then possibly we have some problem. So that, and this limited term should go to 0. And only if when now x is in modulus is less than 1, it goes to 0, so that it is approaching to 1. Right? That's exactly this statement. Here, for y equals 1 over 1 minus x, we try to make a polynomial here. Now start with 1, and that the first term, and now we try to use linear, and now quadratic, and here finally we try to visualize the 8th order polynomial y sub a. Then it is approximating quite nicely. Once you try to choose in a higher order, then it will better approximating the original function 1 over 1 minus x. However, this convergence is done when only the x is between -1 to 1. Okay. Okay, here it follows from example 320 that the example 320 is this one, that a function can be approximated by a power series. And secondly, a power series may converge only on a certain interval of radius r. So here, we have to test the given power series. Once the power series is not convergent, then basically it's meaningless. Not convergent means that the value may go to infinity or oscillatory. Then we cannot use it, and we cannot define the value. So that first of all, we have to make sure the power series converges. Here, let sigma an, so that each term is represented by the an notation, be any series, and suppose that here a n plus 1 over an. In this 1 here, this is a0, whole thing is a1, a2, a3, and so on, right? Okay, we try to measure the ratio of the consecutive the term in the series, and measure the absolute value of this ratio. And as n increases, if it is converging to rho some number, then by using the number, we can here now say the convergence. If the limit is bounded by 1, less than 1, then the series converges absolutely, which means that absolute value of terms converges. Okay. Now, once the limit is larger than 1, then the series diverges. And if the limit is 1, then the test is inconclusive, which means that we cannot decide the convergence by using this ratio test. Let's see example. For what values of x do the following power series converge? Okay. Okay. So here we may say that this is a1, a2, a3, a4, and so on. So let's try to use the power series. Now an plus 1 over an, absolute value. Okay, that is same as absolute value of. Here, an will be, now, there will be either plus or minus, but along with the absolute sign, we'll ignore plus or minus sign. an will be xn over n. Okay, no, an plus 1. So that then must be x n plus 1 and over here n plus 1. That is top, and the denominator must be an, which is x to the n over n. Right? Okay. Now for x term, we have 1x here. Now n is growing, so that now along with these two terms, we have here n plus 1 on the bottom. Now as n approaches to infinity, this term will converge to 1, so that eventually here whole thing will approach to here now x absolute value. So that is rho in this theory. Once we have a limit, then once the limit is bounded by 1, less than 1, so that, okay, that's rho. So rho is now x. If this is less than 1, then we know that the series converges. Okay, that's it. But here, if rho, of course, the same as now absolute x, which is larger than 1, and then we know that that is diverges. Okay, and what if we have rho equal 1, which means that rho equal 1 means here x absolute value equal 1, that means x is now plus minus 1. Okay, in this case, the test is inconclusive. So by using the test, we cannot decide if the series is convergent. So we may try to use some basic technique to decide if it is convergent. So first case is now x equal 1. Okay, x equal 1. Start with that. Then the series becomes here 1 minus 1/2 plus 1/3. Here you are plugging 1 here, 1 minus half plus 1/3 and minus 1/4 and so on, like that. This is an alternating series, and each term becomes smaller, smaller, smaller. Then in some theory, we know that this is convergent. Okay, so when x equals 1, this is convergent. Now, how about x is minus 1? X is now minus 1. Then the given series is changed in this way. 1 minus 1/2. Okay, it's now x is minus 1, so that this term will become here minus 1/3, and again minus 1/4, minus, and so on. And that is same as this one. Okay, you can write down this one in this way, and 2 minus and 1 plus 1/2. Okay, plus 1/3 plus 1/4 plus like that. Right? But we know that here from some theory, this is infinity, is blowing up. So this whole value will go to minus infinity. So when x is minus 1, it's not convergent. So here we can conclude the interval of convergence is from minus 1, okay, that one, okay, between minus 1 to 1, but minus 1 is not included. However, 1 must be included. So here from minus 1 to 1, with 1 included. If you choose x from this interval, then the series is convergent. Okay, for this one, you can do the same. Now, because of that factorial term here, okay, if you try to measure now that one, so that a n plus 1 over a n, absolute value, then that is absolute value of now a n plus 1, that is x n plus 1 power, and that is n plus 1 factorial, and divided by x to the n over n factorial. Okay. Now for x terms here, we have absolute value of x, and for this, we have 1 over n plus 1. This is a multiplication up to n plus 1. This is a multiplication up to n. So we have extra n plus 1. So we reach at that one. Now, as n increases, this will approach 0, which means that now there's rho. No matter what x is, it doesn't matter. This limit is always less than 1, right? That is less than 1, so that for every choice of x, it is convergent. In fact, this one is the same as e to the x, okay? Okay, here, the reason we are using power series representation is here. Once the power series has radius convergence R, that means that this the series is convergent when we are choosing x satisfying this inequality. So its center is A, and here radius R. Inside of this radius R, x is chosen. Then now we assume that is convergent. And we say, because it's convergent, we can name it. So when the f is the name of that series, then here we can get derivative. And term by term, along with the term by term differentiation. So each nth term, Cn x minus a to the n, we can get for this one is derivative. So it's n will come out. Now Cn is constant anyway. N is coming out. Then x minus a power 1 down, which is n minus 1 here. And if we want to make one more time of derivative, second derivative, then again you can do it, and here term by term differentiation, so that here from this one n minus 1 will come out, and then power 1 down, which is n minus 2. In this way, you can get the derivative term by term. So that is quite convenient in many applications. And also, if you try to get integration, and here, if the original function for given function probably is not easy to get integration, but assume it can be written as this power series, then here for the integration of that one, you can get integration term by term from this side. That'll be much easier to reason this anyway. We know the formula. For instance, the integration is opposite operation of derivative, so that from x to the n, here the integration is 1 over n plus 1 and x to the n plus 1. From this one, if you try to get derivative, then you can reach at that. So it is integration. So term by term, you can get integration to get whole integration. So this is really advantageous in many applications. Okay, here a power series is given as in example 3.25 and B, that one, here, this one. And I said that this is practically e to the x. Okay. Now, let's try to find the derivative. We say this one, because it's convergent everywhere, and we name the series as f of x. Okay. Then f prime of x is same as, okay, derivative, it'll disappear, and 1 and plus, okay, 2 will come out, so that will disappear along with this 2. So it is x. Plus, now 3 will come out, and 3 factorial will become 2 factorial, canceling 3, so the x squared over 2 factorial. The next term will be x to the 4 over 4 factorial. If we try to make a derivative for this term, then again, there will be now x to the 3, 4 will come out and cancel with 4 here, and the remainder part is 3 factorial, and so on. Now, here, you can see, you can compare these terms and that one. They are identical. And here from this one, you can say that e to the x, this is e to the x, derivative is same as e to the x. Okay. From calculus, if you were in a calculus class, beginning class, then you already know this one. Okay. And term by term differentiation and integration is quite here useful. And also for some applications, rather than using infinite series, we cut here the infinite series to become a finite the summation, which will become now polynomial. And so that by using the polynomial, we can do some other tasks. So in engineering application, power series technique is so useful. And we'll try to further use it for given function. So right now in this part, we defined just power series, but in the third part, we'll try to find the power series for given function. So that is the topic of Taylor series. We'll continue in the third part. Thank you.